Okay, in this video, we are actually going to run through a scenario and actually run a hypothesis, a one sample T hypothesis test all the way through. I'm going to look at the recipe for success first, kind of break that down because that kind of gives you a step-by-step process of what's going on, and then we'll actually do it. So the very first thing says write your hypothesis, and your null will always be the HO, and if it's a test for means, it'll be mu equals, and this is just the letter M, it's going to be mu equals some numerical value, all right? The alternative will be mu does not equal, or mu is less than, or mu is greater than the same value. These two things have to be the same. Those numbers will be the same. And then the next thing is we're going to define the parameter mu in context. And it's going to be let mu equal the true population mean of whatever it is we're interested in. And it's go so of ... Truthfully, you can switch one and two. That order doesn't really matter. Some people prefer to do the second one first. Sometimes it helps to do this one first. So those two can swap order, doesn't really matter. The next thing is you have to write the conditions. And for this particular test, for one sample T, we have three basic conditions. And you will see these similar conditions on other tests as well. So these three are hypercritical, and I'll try to give you a breakdown as to what they are. First off, you have to have a random sample. Your data needs to somehow be randomly selected. In random sample, and they generally will tell you that, and you'll say random sample, and you write the word given by it and check it off. The N is less than 10% of the population is an interesting one. Several times in the year, I've talked about a giant pile of M&Ms, and I will take an M&M and I'll eat it. And technically, when I do that, the percentage of colors changes slightly. But because it changes so slightly, we don't worry about it because there's a massive pile, and I only took away a small amount. Well, the thing of it is like, well, you have to have a certain size sample. If the sample is too big, it becomes a problem, because then it becomes, because technically when I ate that M&M, it was no longer independent, it became dependent, but only slightly so. And so like, well, how big of a sample is too big? Well, our sample size needs to be less than 10% of the population. And this is generally a check to make sure that it's independent enough, because we are sampling without replacement. And technically, when you sample without replacement, things are dependent. The next thing is our normality, and it shows up three different ways. One, they may tell us the population is normal, or N may be greater than or equal to 30, in which case the distribution of means is normal by central limit theorem. Or if data is given, we're going to have to draw a box plot or histogram or some other to say that it's no skewness, no outliers, and it's normal enough, or okay to proceed with the normal. All right. So either they're going to tell us our sample size is going to be greater than or equal to 30, or we're going to have to draw a box plot. Then we're going to write our equation. I highly recommend you draw a graph and shade based on the information of the problem. Technically not required, but certainly very, very helpful. Then we're going to plug in all our values into the equation. We'll come into something called degrees of freedom. And degrees of freedom for the t-test or one sample is just going to be n-1. We're going to go through all the calculator steps, which are listed right here. And we're going to get a p-value. All right, and we'll state what the p-value is. And if the p-value is less than alpha, we reject the null, and we'll state that. If the p-value is greater than alpha, we're going to fail to reject the null. So here's our statement, our concluding statement in context. Our p-value is whatever the number we calculate, which is right here. We wrote right here. We reject the null if our p-value was smaller. There is sufficient evidence that alpha equal whatever our level of significance, a lot of times this is going to just be 0.05, to suggest that the true population mean, this is the definition from above, is and then we'll restate the alternative. All right, if we have a big p-value or our p-value is greater than alpha, we're going to fail to reject, but it's otherwise pretty much the same. So let's go through one of these. So our problem. The EPA reports that the exhaust emissions for a certain car model has a normal distribution with a mean of 1.45 grams of nitrous oxide per mile. So this is actually the status quo. This is what generally, you know what? Right now, this car model has a 1.45 grams of nitrous oxide per mile. The car manufacturer claims their new process reduces. Well, that's important because reduces means that we're thinking it's going to be less. So that's probably going to be a hint to my inequality. All right. A simple random sample, that's important because that's going to tie into my condition of 28 cars. So this is my sample size is taken. The mean level of exhaust emitted for the sample is 1.27 grams. Hey, we have a sample mean. So this is essentially my X bar. And we know that N equals 28. And we have a sample standard deviation of 0.4. What's interesting to note that this is a sample standard deviation because it's a sample standard deviation tells me I'm using a t distribution. And so our sample standard deviation is 0.4. Is there statistical evidence that alpha equals, so there's my alpha level to support the car manufacturer's claim? So we start off with our null. Our null is the mean of the population, the status quo, what things have always been is 1.45 grams, because that's what it was believed to be and has been. We're trying to see if it has been reduced. They gave that keyword reduced. So they want to know if the mean of the new car is less than 1.45 grams. And let mu equal the true population mean of new cars in grams per mile for the new process. So it might help if I just say this is the new process, because we're not looking at the old cars, we're looking at the new ones. All right. So our first condition, random sample. Well, they told us they had a random sample. They told us a random sample of 28 cars. So that part was easy. The next thing, our sample size was 28. And 28 divided by 0.1, or if you preferred, 28 times 10. And it's always either going to be divided by 0.1 or times 10, whichever you want to do, is 280. It's reasonable to say that there are at least 280 cars of this model. I don't think any manufacturer that's a major manufacturer sells less than 280 cars. I know there's some specialty cars, but in general, they're going to sell at least 280 cars of a model. The next thing is our normality. And remember, our sample size needs to be 30 or larger. It's like, nope, it's 28. But they told us it has a normal. So the population is normal, and that was given. So that's good. So we write down our equation. T equals X bar minus mu S divided by N. So we are looking for, and by the way, I'm going to go ahead and start drawing my picture. My picture went like this. The claim mean, or the mean of the, is 1.45. That's the mu of the population. But we ended up getting an X bar of 1.27. And we had a less than, so we know we're shading off to the left. So this is my X bar. All right. So we're going to go ahead and calculate a t statistic. Well, our X bar was 1.27. That came from the sample. So this is my X bar. This is my mean. Here's my population. That's standard deviation of the sample divided by my sample size. So here's what I do on the calculator. Stat, test, t-test, and make sure we're working with statistics. We don't have our data stored in stat edit. And we're going to go, we have a mean of this case of 1.45. We happen to have an X bar of 1.27. That's our sample mean. We said our sample standard deviation was 0.4, and we had an N, a sample size of 28. Now, when I look at this, I kind of ignore what they write, but I just go, oh, you know what? That's a less than. So I need to choose a less than. So I just drop over and choose the less than. And I say calculate. And I end up getting a t-statistic of 2.38 or negative 2.38. Now, please remember the mean of the t-statistic is always centered at 0, and we got a negative 2.38. You must write down your test statistic. So you had to write this down. So the probability of getting a test statistic of negative 2.38 equals about 0.0122. All right, and you can truncate if you like. Please go to 4 decimal places. So I have a p-value of 0.0123. They told me my significance level or my alpha was 0.05. This is less than. So since it's less than, we always reject the null. And you can we reject HO or we reject the null. That's fine. So our conclusion, which really just comes off of this template, is, you know what, we're rejecting the null, so we're looking at this. Our p-value is, well, we calculated 0.0123 above. Our decision is we reject the null. And then we're going to say there is sufficient evidence at alpha equal whatever our alpha was, which was 0.05, to suggest that the true population mean for, and let me show you where that came from. We actually already wrote it. The true population mean of nitrous oxide in grams per mile. The true population mean for nitrous oxide emissions is less than. Now, let me tell you where this came from. That's exactly what I have here for my alternative, is less than 1.45. So that's what it means by restating the alternative down here at the bottom. It says, hey, restate the alternative. Or it's right here, it says restate the alternative, restate HA, in this case, is less than 1.45. All right, so that's our first example. We will do 2 more examples of one sample T, and they'll move faster because we won't break down the recipe card of the others. Thank you for watching.